Okay, so we shall continue with the shock tube a little bit more, right? Okay, so like we did in the last lecture, so we have, okay, so we have this shock tube, right? Okay, so we had a diaphragm which we break, and so okay, let's do this right back. So this was our diaphragm, right? So this is our shock tube. So this was say region 4, and this is say region 1. This is what we said, and the corresponding values. So then we break this diaphragm. Right, we break this diaphragm, and what we have in that case is that we have a contact surface which is similar to a slipped surface. Okay, so what we essentially have when we break the diaphragm is there is a normal shock, right? Which starts moving into quiescent flow, right? So, and this induces mass motion in this region. So we're going to call this as region 2, right? So we have the contact surface also. So this causes mass motion. So let's say the velocity of that is, say, u, v, and this is obviously right, and on the aft side we have an expansion fan which moves into region 4. So this is basically the shock tube. Now what we're concentrating now is on this normal shock which is propagating. Okay, so let's do that. So therefore now let us just concentrate on this region here. Okay, so we have a shock which is traveling to its right. This is the unsteady. So this is the unsteady shock wave traveling. Now, if we have to convert this to the steady state case that we're most familiar with, then all we will do is superimpose this flow with a velocity w in this direction. Okay, so if we do that, then what we get is essentially now okay, let's sort of redraw that. Okay, so what we get now is that this is the shock wave now. Okay, the velocity of that is now 0. Okay, so velocity of the shock wave is now 0. So it's basically a standing wave, and the velocity here becomes well, then the velocity here it becomes, right, and this becomes w. So this is my region 1, this is my region 2, so this is u1 and this is u2. Okay, so all we've done is taken this and imposed a velocity w in the other direction. So what that gives us is a velocity w in here and a velocity w minus up here, and this is my steady wave, right? This is a steady state. Okay, so this is what we did in the last lecture. So what we did is we wrote out therefore, so therefore w1 is this, and u1 is w and u2 is w minus up, and using these we wrote out the three governing equations, right? And we were also able to write the Hunio's equation, which turned out to be exactly the same for both these cases, right? So now let us look at some things here. Now we said that this velocity, let this velocity up is going to be less than w. Okay. Now, so the question to ask here is that, is there basically an idea, or can we estimate how much up will be depending on the speed of this shock wave? Okay. Let's see. Now, let us write down the moving shock wave. Okay. So, right. So, the shock wave is basically moving into this quiescent region. So, the shock wave Mach number we can write like that, and then I can or I can also sort of rewrite this in this form, which is okay, without really going into the descriptions, okay, or basically, okay, basically this is equal to just a little space. Okay, so what we have is okay, so like we said in the last lecture, is that basically the shock here, the strength of the shock is governed by the pressure ratios across it, right? Unlike in the steady state case where we deal with basically the incoming Mach number, right? So this is the Mach number of the wave, and therefore I can also write this. So therefore W is basically A1 into this. Okay, so in that case, so okay, let's sort of write that. So therefore W is equal to A1 into this. Okay, so this is it. Now let us write UP. Okay, now UP can be written like this. So this is all from the governing equations. So you can just sort of cross check this if you so want. Okay, let me sort of move this space. Okay, so UP can be written as okay. Using the three governing equations, we can, just come up with this. I'm not doing the math, which by this time, hopefully, you should be able to do that. It's preliminary elementary. Okay, so this is more or less this is the expression for UP, and you can see we've written it out essentially in terms of the velocity of sound in the driven section, which is section 1, and the pressure drop, pressure ratios between the two sections. Now let us see what now. So basically, so this is the region. Okay, so this is the region in UP is functioning. So if I have to write this UP by A2, now we can write this as UP by A1 to A1 by A2, right? So that will also be okay. Now the reason I do that is because then I can write all of this just in terms of P2 by P1 and gamma, right, which is what we get, right, which is what we get, and therefore UP by A2 comes out to be this. Okay. So this comes out to be this way. Okay. Now let us do a little bit of math out here. Okay. So now just for the ease of working with this sort of a little elaborate expression, let's just denote this. I'm going to just call it theta. Okay. It's just, there's no physics in here. It's just I'm representing this as another variable. Okay. It's just a dummy variable. So if I do that, what I get is this. Okay. Okay, so that's the second term, and then we have this, which is okay. So we do that. So now I'm going to do something one more step out here. Okay, I'm going to write this like this. Okay, I do that. Then again, what I do here is that basically I take theta out. So what I get here is 1 by root of theta, so I get 1 plus right. So hopefully you can see what I'm doing. So what I did is took theta out of this bracket here, so what I get is this. Then again from the denominator I take a theta out, so then I get this here, and this expression becomes like that. Notice we have a square root, so hence the root of theta here. Okay, so we do similar stuff over here. So what again I get okay, I take theta out from the numerator, so I get this. Okay, and I take theta square out from the denominator, so then I get this. Right, so get 1 by theta, so what we get out here is this, right. So this root theta cancels with this, right. So let us just cancel that out. Okay, so now that we have this expression, now let us look at this. So what we are basically saying is that theta is this. Okay. Now let's just say that this tends to infinity. It's infinitely large. What that means is that we have an infinitely large shock propagating, right? Because that depends on this. So larger the pressure ratio between the two regions. So let's come back in here. So P2 minus P1, so the larger the pressure ratio between these regions, you have a larger shock which is propagating. Okay, so let's just say we will take as an infinitely large pressure ratio between these two, which means that this, say mathematically, this is tending to infinity. If that is so, then what happens to this? That tends to what? Okay, what we get there is this becomes 1, okay, that becomes 1. Then in here what we get is 2 gamma by gamma plus 1. At bottom we get 1. This is square root. Okay, what we get over here is again 0, right, and 1, and what we get is this. Okay, so let's just say we write it a little better here. So what we get, 2 gamma by gamma plus 1 and gamma plus 1 by gamma minus 1, right? So what we get over here is essentially this. So this tends to what this tends to is basically 1 by gamma into gamma minus 1. Is that right? Okay, let me just sort of cross check that. Or sorry, yeah, we have the 2. So it's basically 2. So 2 by, yeah, so that's what it is. So what we get is this. So what we're saying here is that for an infinitely large shock, if you have an infinitely large shock, the Mach in the region behind it, right, tends to this. Okay, so if for a given gamma of say 1.4, so therefore this becomes 1.89, which is less than 2 Mach, right. So what this tells us that if we have an infinitely large shock which is propagating, then the velocity which is induced in the dry section here, the velocity which is induced reaches a maximum of around 1.89. Now that is which means that the Mach number of the different section, so this is the maximum. So the maximum value of this is 1.89, which is less than 2 Mach. Okay, so basically the Mach number of the induced flow, it cannot exceed more than 1.89. Okay. All right. Now, so that is a little bit about the incident shock waves in the shock tube. Now let us sort of move a little further and see something else. Now, okay, so now that we have this, right, so we have this incident shock here, okay, and this is the steady case of this. Okay, now let us look at another picture. Now what happens is now this shock, okay, this shock is moving into the tube, right. Now you can think of this, that suddenly we close a valve in this region, right, or say this hits against this wall and then it reflects back. Okay, so usually in various industrial applications, there is a sudden closing of a valve, and what that does, it creates a reflected shock wave in the other direction, right. So if you have say something like that, this is traveling right into the tube, and there is a sudden say closing of the valve out there, then what happens? Well, so what will happen is right, I still have this. This is my region 2, and then this shock, okay, meets that region, and it's reflected back, and obviously the strength of that is now different. It's not the same as W. So say it starts moving in this direction, and let's call this as WR, okay, and let's call this region, okay, let's call this region as 5. Again, here also, because it comes to a very sudden stop, or if maybe even if it's hitting the wall, it's basically comes to a sudden stop. So the flow velocity here is 0. Okay, so this is essentially the reflected wave. Now, again, this is essentially the wave picture, okay, of the reflected wave. So we can, of course, convert this to the steady state case by imposing a velocity which is exactly in this direction. Okay, so this is what we have over here. Okay, so now. Again, this is the unsteady case, and this is the, so let's just say that this is the incident shock. Okay, this is the incident shock, this is the reflected shock. Okay, this is a reflected shock. So let us just convert this to a steady picture of that. Let us do that. So if I had to do this, okay, so again, okay, so we have the shock wave out here. So this is moving this way. So now what we will do is impose the whole flow with a velocity which is this, in this direction. So what that would mean is that the velocity of the shock wave, the velocity of the shock wave, of the reflected shock wave is 0. Okay, that is 0, and then of course okay, so this is region, say, 5, and this is the region 2. In that case, what we get is UP plus WR. Okay, so this is equal to, say, this, and U2 is this, and U5 is equal to WR. Okay, U5 is equal to WR. So that's all there is. Now, how do the governing equations look like for the reflected shock wave? So all we need to do is therefore input these velocities, okay, into those. So therefore, what we had for the governing equations, if we were to go back there, so what we had is rho 1 u1 is rho 2 u2, right? So in that case, what this will become is, so what that becomes is that rho 2 up plus wr is rho 5 WR, right? So that is the continuity equation. Then similarly, so that this is the continuity equation. So then we have the momentum conservation. So similarly, so this then becomes P2 okay, and that is equal to P5 okay. So this is the momentum conservation, and finally we have the energy equation. Okay, so if we have this, so then this gets transformed to okay, and that is equal to okay. So this is what we get from the governing equations. Okay, now the question is, okay, we have two more relationships. If you remember here, we had two more relationships. For example, for the incident shock we had this, right, and for the reflected shock then we shall have okay. So now for the incident shock, if you look over here, this is for the incident shock. So the Mach number of the incident shock was W by A1. So if you look at this steady state picture here, we have a flow coming in, it's intersecting the shock and moving past it. So this is the Mach number that we are concerned about, right? So this is W by A1 in this region. Now for the reflected shock, the steady state picture looks like we move from here into this region, right? So therefore this is the shock Mach number that we are concerned with, this region. So that is WR plus the velocity there is this and A2. So this is the Mach number of the reflected shock wave. Now these are the relationships that we know. Now if we use these two relationships, we can see that we can get some relation between the reflected shock Mach wave and the incident shock Mach wave. So what that means is that for a given incident shock, I will have an estimate of what sort of shock the reflected shock will be. Okay, which in turn means that if I am aware of the pressure ratios between 2 and 1, right, between these two, the driven and the driver sections, then I have an estimate of the nature of the shock, okay, which in turn gives me an estimate of the nature of the reflected shock. So again, without getting into the elaborate derivations, let me sort of write this out. Okay, so then what we get here is, this is a kind of an expression that we get. Okay, so this is the relationship between the incident shock Mach wave and the reflected shock Mach wave. Okay. Okay, so this is essentially the relationship between the incident shock Mach wave and the reflected shock Mach wave. So if we know this, then we shall have an estimate of this. So let us sort of do a small problem based on this and see what exactly we are talking about. Okay, so the problem says that an incident normal shock, okay, reflects from the end of a shock tube wall if the air in the driven section, right. So this is the driver section, right, because the shock is moving into the right. So this, as we had said in the last lecture, that the pressure out here P4 region is much more than 1. So therefore when we break the diaphragm, it moves into the quiescent flow here. So therefore this is the driver section, this is the driven section. So the air in the driven section of the shock tube is at P1. So P1 is given as 0.01 and T1 is 300 Kelvin, and the pressure ratio across the incident shock is 1050. Okay, so let's say what is given. So the problem here, P1 is given as this, okay, and T1 is given as 300 Kelvin. Okay, this is given, and the pressure ratio across the incident shock, which is quite large actually. So the pressure ratio across the incident shock, if the way you choose to look at it, if you look at say the study study picture of this case, so basically I have a flow which is moving across a standing shock. Okay, so the pressure in this region is given, P1 and T1 are given, right, and the pressure ratio between P2 and P1 is given as 1050. So what we need to find out is calculate the shock wave velocity with the reflected shock velocity with respect to the tube. So therefore we have something like this. So we have an incident shock moving, there is a sudden closing of a valve, and we have a reflected shock propagating. So what we need to find out is the reflected shock wave velocity with respect to the tube. Okay, now you have to remember that, because the reference frame with respect to the tube and outside it in the laboratory is going to be different. Okay, and pressure and temperature behind the reflected shock wave. So pressure and so behind the shock wave, which will be in region 2. So in that case, how do we go about this? Okay, so we will basically look at this picture out here. This is for the incident shock, so we will look at this picture over here. So in 2 region, I can, this is my velocity and this is my velocity, right. Now what we can find out here is the A1, which is gamma r T1, right. So then taking gamma to be 1.4, so what we have is 1.4 287, and T1 is given to be 300 Kelvin, right. So this comes out to be 342.2 meters per second. So I get this, right. Therefore what I get from here is the incident shock Mach wave, isn't it? So that is W by A1. Okay, so what I get is W by A1. Now how are we going to get, I have A1 here, how do I get MS, because we do not know W. What we know however is P2 by P1. Okay, the problem that we did last class, so we calculated the incident shock Mach wave. In this case what is given is P2 by P1. Okay, now this P2 by P1 corresponds to this incident shock wave. So therefore we just go and look at the normal shock tables corresponding to P2 by P1, which is equal to this. We find out the incident shock Mach wave, the Mach number, okay, which in this case comes out to be 30. Okay, 30. How do we therefore calculate? Now that we know this, let us use this relationship here, which is the relationship between the incident shock Mach wave and Mach number. Okay, we put this value in there with a gamma of 1.4, then we will be able to get a value for MR. Okay, so without going into the details of that calculation, what I get from here, the reflected wave I get as 2.65. Okay, so now basically this is so reflected wave shock wave, I get 2.65, right. So now basically this if I say look at this picture over here. So now we need to find out the reflected shock wave velocity with respect to the tube. So with respect to the tube, we need to find out the reflected shock wave. So which is, if you look at this picture here, okay, if I look at this picture here, so what I can find out, so I know A1, right, I know yes, I know A1, so therefore I can calculate the velocity of the reflected shock as A1. Okay. Now, having done that, what we need to calculate are the pressures and temperatures behind the reflected shock. So this is the reflected shock. So behind the reflected shock is basically in this region. Now this region is quiescent, because again it initially the shock was moving into the quiescent region, and again this it has brought to a sudden stop, and it sort of moves in the opposite direction. So this P5 in here, so P5 and T5 are basically equal to P1 and T1, right. Now corresponding to this Mach wave, Mach number, so corresponding to this Mach number, again we go to the tables and find out. So basically P2 by P5 actually, and T2 by T5. Okay, and then we shall be able to calculate the pressure and temperatures, because like I said, P5 and T5 is equal to P1 and T1. Okay, so that's a small problem basically to see what we mean, you know, by this, how we're going to basically calculate, you know, these properties. Okay, so now let us look at something a little more interesting. Okay, over here. Now let us go back to this picture over here. Okay, so let us look at these two pictures. So we have an incident shock. We have an incident shock, okay, which propagates, and then it reflects from the end of the wall, and it propagates in this manner. Okay, so so what we're going to look at is essentially what is happening over time, right. So this is essentially an unsteady case, isn't it? So I have things traveling, say in the direction of, in this direction, isn't it? So say I have this is say x direction, okay, over a period of time. Okay, now at t is equal to 0, okay, there is nothing. So basically t, we can say that, you know, I am here. So essentially say I am at this point. Okay, now at t is equal to T1, say the diaphragm is broken and we have a shock wave which starts at some instant of time. Okay, so just about, you know, at t is equal to 0, say, you know, little bit away from that. So the diaphragm is broken and we have a shock wave traveling. So say the shock wave travels for around, say, T1. Okay, so this is a picture, for example. So this is a picture, for example, say let's just say that this picture that we are seeing is at a time T1. So what has happened is that this has traveled a certain distance, the shock wave. Okay, so say at time T1, okay, let's just say this is a time T1. Okay, this is time T1, okay, and at that point it has traveled a certain distance, say, which is x1. Okay, so therefore what we see here is that I am at, say, this location. So basically, therefore, right, so if I may call this as, say, let me call that at A. So the A point, the point A in that xt diagram is essentially this picture here, right. At 0 there is no shock wave, and just just at that point we break the diaphragm, the shock wave starts traveling, and this is a picture that we are seeing at, say, some time instant t1, okay, when the shock wave has traveled, say, a distance x1. So at time t1 it has traveled a distance x1, so this is the xt diagram, right. Now after that, again, what happens is, at say time t is equal to t2, it hits the end wall, okay. So basically what happens is that it travels some more distance and hits the end wall, okay. So the reason we do that is because this is going to continue, isn't it? The same slope is going to continue because the same velocity is going to continue, is going to travel with the same velocity w, right. So this is essentially, so this is the incident shock, this is the incident shock, and then so at time, say, t is equal to t2, right. Okay, so at time t is equal to t2, it hits the end wall, say, which is at a distance, after traveling, say, a distance this much. Okay, so let's call this point as B, right, and then this is the point. So therefore this is essentially the incident shock, okay. So this is the incident shock. So this is the end wall, this is the end wall here. Now after this, what happens is that there is the reflected shock, okay. So the picture that we see here, so at this point here there is no reflected shock, but the moment it hits this, immediately after that there is the reflected shock, and this is what we are seeing at, say, time t is equal to t3. The picture that we see here is at t3 when the reflected shock has again traveled with some distance, okay. So now let us say at time t3, so this is t3, okay, and so basically now the origin of the reflected shock is going to be here, okay, at this point B, right, but the velocity of the reflected shock is going to be different, okay, than w. So therefore the slope of that is going to be different. So say therefore it travels by some distance, okay, so travels by some distance, and say which is here. So essentially what I am saying is it travels from here in the opposite direction like that, okay. So let us just say it travels by some distance xr, the origin now being here. So therefore what happens is that so therefore I have this reflected shock wave, okay, and this is essentially, so therefore this is essentially a okay, let's call this, so this is the picture that we are essentially seeing, okay, xr, and this is the reflected shock, okay. So this in here, this is the right, and velocity is wr, which is not equal to w, which is not equal to the incident shock. So this is what we see over here, Okay. Now, so therefore, this is basically the X-T diagram, and if you have a plot like this, you can see pretty much the the way the shocks are moving, etc. Now let us also look at this with in a different perspective. Now, say in the shock tube, okay, at a location x1, okay, at a location x1. We have a particle, right, which is sitting here, okay, and what happens then is just sitting there. It doesn't move, right? It doesn't move. It just sits there until this incident shock meets it, isn't it? So it meets it at time t is equal to t1. So therefore, I have this particle. I have this particle which is sitting at this distance x1. It continues to sit there for a time t1. There is no velocity there. It just sits there. Okay. It continues to sit there. So let's I'm going to call that as say. Okay, it sits there like that, and after that, okay, so after that what happens is that there is a shock, the shock reaches it and displaces it from its position and imposes a velocity up into it. It causes mass motion. So then it starts moving with a velocity which is up. Now that up, as we said, the slope is less. The velocity is less than that of the incident shock. So then let us just say it moves with this velocity, it moves like that, okay, it moves like this. So this is my up, which is less than the incident shock. Now what you can see out here is that this particle, as it is traveling here, because it has been displaced from its position due to this incident shock, okay, again it meets the reflected shock, which is what you are seeing over here. So again it meets this reflected shock, right, it meets this reflected shock, and the shock is reflecting because there is a sudden stop, so that the entire fluid here is going to come to a stop. So the moment the particle comes here, intersects the reflected shock, it again stops completely, right. So therefore the velocity out here again will be this. Now it has reached the region 5, which is again equal to 0. Okay. So essentially, so this is kind of a little graphical way, or an interesting way to kind of understand the functioning of the shock tube. Right. So what essentially this diagram is giving us is a picture of the movement of the various shocks out here with respect to time. Okay, because this is an unsteady case. Right. So we found out relationships between the thermodynamic variables, etc. But what this is giving us exactly, that what is happening at various instants of time along with the in the particular directions along the length of the shock tube. Right. So again here basically what you can see here is that you have a therefore this could also call for interaction of shock waves, because you have this incident shock wave, right, that reflects. Okay. So and what you see over here, that this is a fluid particle which was originally at rest. It was displaced from its position by the incident shock, and it starts traveling with a velocity up, which is less than that of the incident shock. It is traveling and would have reached the end of the tube, but before that it intersects another shock wave, which is the reflected shock wave. And what that does, it completely stops this particle in its path, right, and therefore the particle again continues to being at a stop. So therefore the particle basically has been displaced from this position x1, so say to the position xp. So essentially the particle has traveled from x1 to xp in given this time. Okay, so that should be all. Thank you.